In a steady flow system, the rate of flow of the working fluid is constant with respect to time. That is, the mass that flows in is equal to the mass that flows out. So the mass flow rate is going to be a constant. Similarly, the energy that goes in is going to be equal to the energy that goes out of the system. So as we can see in the diagram, so it is an open system or it can also be a controlled volume. So the mass of fluid that enters inside the system can leave the system only after it does work. So before deriving the energy equation for a steady flow process, let's try to understand the different forms of energy. The first type is stored energy, the second type is transit energy. Stored energy are contained within the system boundaries, like potential energy, kinetic energy, internal energy, whereas transit energy crosses the system boundaries. So these are heat, work, electrical energy, etc. So a simple example for stored energy is given here. So you can see the object on the cliff. While the object is at rest, it has only potential energy, whereas after the object starts falling down from the cliff, the kinetic energy increases and the potential energy keeps on decreasing. So, transit energy, you can see the diagram at the bottom where we have different forms of heat, that is, radiative heat, conductive heat, convective heat, that is being transferred from the heating coil of the stove to the pan to the handle to the water. So, the different forms of heat energy are crossing different boundaries here. That is the boundary of the heating coil, the pan, the water. Then it heats the air. It can come to the handle and to the human hands that is holding the pan. So, potential energy, as we know, is mathematically given as mass times the acceleration due to gravity times the height of the system from datum. Kinetic energy is possessed by a system because of its motion. So, kinetic energy can be given mathematically as half mass times velocity square. So, all these energies have the same unit, that is joule. So, energy that is crossing boundaries is called transit energy, whereas when a mass crosses boundaries and there is an energy associated because of this mass crossing boundary, then this energy is called flow energy. So, in this case, the displacing mass must do work on the mass that is being displaced. So, let's say a mass is entering, and because of the mass that is entering, the same amount of mass of fluid has to leave the system because the mass flow rate here is a constant. So, the displacing mass must do work on the mass that is being pushed out or being displaced. To represent flow energy mathematically, so we can write it down as flow energy is equal to force into distance moved. So since flow energy is associated with fluid, so we can write force in terms of pressure. Pressure is equal to force applied over an area. So force can be equal to pressure into area. So we can write the flow energy as force, that is pressure into area into the distance moved. So this area into distance can again be written as volume or volumetric flow. So the flow energy equation becomes pressure into volumetric flow and the unit is Newton meter. So the unit of volumetric flow rate of the flowing fluid is given by meter cube per second. So for unit mass, flow energy is given by pressure into volume, and the unit is Newton meter per second or joule. And also, the total energy of any system is the sum of all energies. That is, total energy is equal to kinetic energy plus potential energy plus flow energy plus internal energy plus it can be heat or work or any kind of energy that is associated with the flow process. So before deriving, we need to understand the assumptions in steady flow process. So the mass flow through the control volume is constant. The rate of heat transfer is a constant, rate of work transfer is constant. The state of working fluid at any point is also a constant, and we consider only energies like potential energy, kinetic energy, internal energy, and we do not consider chemical energy, electrical energy, or magnetic energy. This diagram represents a simple form of steady flow process. So you can see inlet is represented by 1 and outlet is represented by number 2, and we can see the height of inlet and the height of outlet are represented by Z1 and Z2 from the datum level. Similarly, all properties or all values corresponding to the inlet will be given with a subscript 1. For example, pressure, specific volume, velocity, then specific internal energy, height above the datum level is all going to be given with the value 1 or subscript 1, whereas the values of working fluid at the outlet will be given with subscript 2, and heat supplied will be represented by Q and work delivered by the system will be represented by W. To derive the steady flow energy equation, let's write the total energy entering the system. That is, total energy is equal to potential energy, kinetic energy, internal energy, flow energy plus the heat supplied. And the total energy exiting or leaving the system can be written as potential energy plus kinetic energy plus internal energy plus flow energy plus work delivered by the system. As we can see, the total energy can be represented mathematically, and we do not have the mass in any of the energy here because energies are all considered for unit mass. So same thing can be said here at the outlet. So the energies are considered per unit mass. And we know by the law of conservation of energy, the total energy entering the system will be equal to total energy leaving the system. So we can equate the energy at the inlet and the outlet like this. So we have a mathematical expression where we have the potential energy at the inlet plus kinetic energy at the inlet plus the internal energy at the inlet plus flow energy at the inlet plus the heat supplied, which is equal to the potential energy at the outlet plus the kinetic energy at the outlet plus internal energy at the outlet plus the flow energy at the outlet plus the work delivered by the system. And we can also see enthalpy hidden in this equation, that is internal energy plus pressure volume product. So same thing on the right hand side. So we have enthalpy here. So this whole expression becomes potential energy plus kinetic energy plus enthalpy instead of internal energy and flow energy on the left hand side and the right hand side. And this equation 1 is called the steady flow energy equation. Now if we change the units of the energy, unit of heat and work, the equation can be changed further. For example, if we are going to express flow per unit mass, if we are going to express it in terms of mass flow rate m dot, then we'll have to multiply the mass flow rate throughout the equation. Then the equation becomes mass flow rate into left hand side is equal to mass flow rate into the right hand side. If the values of Q and W are kilojoule per kilogram and the enthalpies unit are kilojoule, then the equation will become potential energy divided by 1000 plus kinetic energy divided by 1000. So same thing happens on the right hand side too. So mass flow rate into the sum of potential energy, kinetic energy, enthalpy and heat supplied in the unit kilojoule per kilogram. And on the right hand side, mass flow rate into the sum of potential energy plus kinetic energy plus enthalpy plus work delivered in kilojoule per kilogram. Similarly, if we are going to write Q and W in kilowatt, then again the expression will be changed.